Okay, everybody, good morning. Believe it or not, the speaker has broken in Convocation Hall. So I am going to be using my voice, meaning we're all going to have to be a little quieter in order to hear me at all. So hopefully you can hear me right now. Yeah, there's nothing going on. I don't know if the video can hear me, but I'm wearing the microphone because I think it does get onto the recording, so the recording should be okay. So good morning and welcome, and happy birthday to Alvin, who says he's celebrating a lonely birthday in Toronto for the first time. I wanted to talk a little bit about finishing off the stuff with Chapter 5 on Kepler's laws, because one of the problem set questions actually deals with Kepler's third law, so I think it's good for you to know that. Also, Arshia reminded me on the survey this morning that October is Islamic History Month in Canada, so and it's important. We start, we go on to Galileo, Kepler, and Newton is really the sort of story that the textbook goes through, but it is important to know that all of these three people had books that were coming from Cairo and from the libraries in Iraq and Iran, where there was a lot of physics research being done for many hundreds of years before Galileo turned his telescope to the sky. But that was sort of what happened in Western Europe. The order of events was first Galileo started drawing pictures of things like the moon and craters on the moon, and he really realized that this was a place with mountains and craters and things. He also looked at Venus and saw Venus go through phases as if it was orbiting the sun. And he also looked at Jupiter and saw the moons, the 4 Galilean moons of Jupiter that were clearly orbiting around Jupiter. And a lot of this really flew into the face of the basic paradigm of science at the time, which was that the Earth, feeling stationary, was at the center of the universe, and the stars in the heavens were kind of all orbiting around the Earth. It really didn't look like that from Galileo's telescope perspective. And then Kepler came along. It was sort of around the same time as Galileo, but in a different part of Europe, looking at, not through a telescope, but just looking at very careful observations of the positions of the planets in the sky. It was really just a long tube he was using without a lens, but was able to measure altitude and azimuth of planets over many, many years. And so they came up with the laws of planetary motion, which I'll discuss in a second. Kepler's laws were empirical, meaning that they were really just mathematical equations that he wrote down to describe what he was seeing, but he didn't have a real theoretical underpinning of what was going on, what were the reasons or causes. And so it wasn't until sort of a generation later that Isaac Newton came along and was able to pin down the whole thing kind of more theoretically. You guys able to hear me okay? See how long my voice holds out. So this is a picture of Galileo, and these are some of his drawings of the moon. So that's the moon. So these are the three main observations I mentioned. The moon seems to be a place when you look at it through a telescope. It's kind of fun to do that. Venus not only goes through phases, but another interesting thing is that it changes its apparent size in the sky. And when it's in its crescent phases, it's much larger than when it's in its full phase. And this kind of goes along with an idea that if Venus was orbiting around the sun, then you would expect that when we saw it in its crescent phase, so most of the opposite side of Venus is illuminated by the sun, that's when it should be closer to us and therefore take up a larger angular size on the sky, which makes sense, right? And then when it's kind of on the other side, farther from us than the sun, we would see more reflected light from that near side, and so it should be smaller. So that was kind of nice. And then these are little drawings. The little teeny asterisks are these stars that seem to orbit around, or at least swish back and forth around Jupiter. And Jupiter looked like a little disk when you look at it in a telescope, and he was able to see these moons who were clearly doing some kind of an orbit around something that was not Earth and not even the sun. So, and at the same time, Kepler was looking at careful observations of the apparent positions of planets in the sky. So it was determined that the planets, including Earth, orbit the Sun, and that the Earth is the third planet from the Sun, after Mercury and Venus. Kepler also noted that the paths of the planetary orbits, especially Mars, he found out, were not exactly circular, but a little bit, there was a new mathematical shape called an ellipse. So if you take two tacks and wrap a string around them, and then pull the string taut with a pencil to make a kind of triangle, you can trace out a mathematical shape called an ellipse, which is defined as the locus of points that is the sum of the distances from the two foci is constant. So, and you know, Pluto is one of the more eccentric orbits, but so there's something called the semi-major axis of an ellipse, which is like half the major axis. And the eccentricity tells you how squished the orbit is. So a special case of an ellipse is when eccentricity equals 0. And actually, there was a question this morning on the Precast survey. I thought, you know, why do we consider the Earth's orbit to be perfectly circular? Well, so the orbital eccentricity of the Earth's orbit is 0.0167. Turns out that perihelion happens on January 3rd, and aphelion happens on sort of July 3rd, which is maybe a little surprising since it seems to be so much, we're actually closest to the sun in January when it's clearly a lot colder here in the northern hemisphere. But so what's causing the seasons is not the actual slight change in distance by 3% of the Earth from the sun, but it's all about the tilt of the Earth's orbit relative to its orbital plane. There's a 23-degree difference between the spin axis of the Earth and the orbital axis of the Earth. And what that means is that for half the year, the northern hemisphere is kind of facing the sun more and gets longer days and also more direct sunlight. And then the other half of the year, it's the southern hemisphere that gets a little higher, sun's higher in the sky and days are longer. So that's why I guess it's just something we can kind of neglect is the orbital eccentricity of the Earth, and so it's often considered, I guess, to be approximately circular. But here's the three laws, and the third one is the one that you need, I think, for the problem set. But Kepler's first law is that it's these ellipses, and every ellipse as a mathematical point has two foci, and the sun is at one of those foci, and then the other focus of elliptical shape of the Earth's of the planet's orbit there's just nothing there. Second law is about the speed of these orbits. So it turns out that when planets are closer to the sun in their orbit, they're moving faster, and they get slower when they're farther away. And this actually has to do with the acceleration, and you would expect the acceleration would increase as you're getting closer to the object that you're gravitationally attracted to. And so this was one of the keys that Isaac Newton looked at to think, well, this has really got to be something to do with this gravity force. But so actually, let's read it. A line drawn between the sun and a planet sweeps out equal areas during equal intervals of time. So what that means is that if you look at this dB, this distance from here to here, and compare it to dA, this distance from here to here, then area of A equals the area of B when the time TA equals time TB. So equal areas and equal times. The only way that works if these triangles have different heights is if it goes farther. So what it means is that dA is greater than dB. And what that means is that the velocity, the speed, VA, is greater than the speed VB. It's sort of a nice, like, little mathematical way of just saying, okay, planets go faster when they're closer to the sun. And third law, this is the one that's important for the problem set 4, I guess. There's a question, I can't remember which question it is, but it's one of them. It actually asks if you change the radius, I guess, or the semi-major axis length, which is r, and you look at the orbital period, which is t, so So this equals t, this equals r. Then t squared equals c times r cubed. So what does that mean? It means that when you look at different planets, and they all have different orbital periods, you see that the orbital periods of the farther planets are larger. So the year, I guess, of Mercury and Venus is less than an Earth year, and the year of Mars and Jupiter is longer than Earth's year. Because the farther away you get, so as you increase r, you also increase the orbital period. But it actually goes as, I guess, the period squared goes up as the radius cubed. And so all of these things were just noted by Kepler. And Kepler was a mathematician who had a lot of data, and so he came up with these kind of laws, but they are empirical, meaning that, well, I guess it's almost like these equations we wrote down for friction. Remember I wrote down that the kinetic friction was the mu times the normal force. I never really told you why that is, and I don't think I personally understand why that is. I guess it does seem to me like if you push your hands together, there's sort of more of a force from friction than if the normal force is less. But it's not clear to me why they should be proportional or where this mu sub k comes from. But you just write it down and apply it to experiments, and it seems to work pretty well. So it's an empirical law, which doesn't come from anything else. And I think these Kepler's 3 laws are kind of like that. They do work, they do seem to be true, but they didn't come from something more basic. Kepler did not know why planets moved this way. Well, it was actually Edmund Halley, who studied Halley's Comet, who suggested, was the first to kind of suggest among his community that there's some sort of inverse square law that must be coming from the sun, like a pulling force. And it was Halley who actually was pestering Isaac Newton to publish his results and to try to give a simple theory, some sort of underlying simple theory which explains Kepler's laws. And that's exactly what Newton did. It took more math than Kepler had to figure this out. You needed calculus, which didn't exist before Isaac Newton kind of invented it. And the Newton's law of gravity, this sort of fourth law, is that this gravity force is m1 m2 times g divided by r squared. Once you combine Newton's 3 laws of motion, which we're really familiar with, and then this fourth law, which is that gravity force, these all end up predicting exactly what Kepler's 3 laws. Found one? Okay, that's good. All right, demo's coming together. And then I guess the last thing is just that you expect the moon to orbit in an elliptical path around the Earth, or satellites to orbit an elliptical path around the Earth. And in fact, the parabolic trajectories of just objects that you can throw, like this, this tape, this is part of an elliptical orbit around maybe the center of the Earth. But it looks like a parabola when you kind of view it really close up. Parabolic trajectories are parabolic in the approximation that we can neglect the curvature of the Earth's surface. So it's sort of like this little bit of a flat Earth perspective. But the center of the Earth would be one focus, and it would be sort of at the other side. I think that's now chapter 5. It's weird without the microphone, but it must be bad in the balconies, I guess. I don't know. Can you guys hear me okay up there? Way up there? You can. Okay. I'm seeing some thumbs up. All right. Great. We're on to chapter 6, it's all about momentum. And you might have done the pre-class quiz, which asked you some questions about momentum. But it starts with this analogy. So I'll give you a little top hat question about that, which is to do with the analogy of conservation of mass and conservation of momentum. And it might be a little confusing because they're not related really, but it's the idea, I think if you break a plate and it goes into a lot of little pieces, you can imagine that you can gather up those pieces and sort of form yourself a plate again. And if there was one big shard missing, and you could see it sort of not there, you would look around more on the floor until you found that extra shard. Maybe it went under the stove or something like that, and you would eventually find it. So we have this sort of feeling that mass should be conserved. And when a process such as smashing a plate happens, things don't just disappear. They just move around. And so, and it's the same thing with burning. If we choose the log as the system, certainly then it seems to go away and the mass of the ash is less. But what we didn't take into account is all the smoke and steam that comes off of, and carbon dioxide gas that comes off when you burn something. And so the law of constancy of mass in an isolated system is that when a system of objects is isolated, like maybe you put it inside a closed flask, then as chemical reactions occur, the total mass of the system doesn't change. And that's what you're hopefully looking at on your top hat right now. If 18.02 grams of water are separated by electrolysis into the two component gases that make up water, hydrogen and oxygen, and you've created 16 grams of oxygen gas, how much hydrogen gas would you expect to have created? Okay, you guys got it, pretty much. See if I can go to laptop 2 here. It just says checking connection. Trying to reconnect.
I haven't seen that before. So we're on laptop 1 here, I think. Yep.
We're trying to go to laptop 2. This is laptop 2. Do you want to go back to?
Don't want to log off because I'm afraid I won't be able to log back on.
I guess one thing I could do is just take the HDMI and try to flip it. Do you want to try to do that?
Yeah, it's better than nothing. Yeah, let's try it.
So what I would take this
Yep.
and try to plug it into
this one, I guess.
take that one
Oh, this
and plug it into wherever.
Oh, I see.
You see what I mean? And plug it into here
Plug
maybe.
it to here.
Yeah. Want to?
Let's see what happens. Maybe this is them fixing the speakers. Okay, well that will work. If you need me to come up and fix it again, let me know.
Okay. Second weird technical glitch of the day. It's fixed. But yeah, basically, the main equation that we end up using in Chapter 6 and in Chapter 7 is that something final equals something initial. And sometimes there's an extra like delta that goes in there. But yeah, basic idea is you've got 16.00 plus the final mass of the hydrogen equals 18.02. That's kind of the way I like to draw it out. So MH equals 18.02 and then minus the 16.00. So, so you've got initial mass, another way of writing it, initial mass plus the delta of the mass, new mass entering the system, or leaving, I guess, if delta m is negative, equals the final mass. Okay. So mass is an example of a conserved quantity. So a conserved quantity is constant in an isolated system. Yeah, how are we going to show the video now, though? We're not going to, right?
Switch. This is what I was thinking.
Because I want to do the demo now. Well, I can show it on this screen. So there are a couple of observational experiments that I wanted to do that come straight out of a textbook, and I brought a video for it, or I brought the carts. Do you want to switch me? Thank you, man.
No problem.
Jonathan's going to work on actually trying to switch this, but I'm just going to stand over here. And we're going to be playing around with this next week. So actually this week in practicals, you're doing all kinds of stuff with circular motion, Chapter 5 stuff, to help you with that, and also the problem set 4 on Chapter 5. And then next week we'll be doing some collisions. Oh, look at that. Thank you. which is this chapter 6 stuff. So, observational experiment 1 is you start with a cart which is at rest. We'll call this cart B. And then cart A comes along from the left and collides with it. And they're set up right now to magnetically repel one another. So there's little magnets, and you'll have these in your cart, but this one doesn't want to stop you. Okay, so this comes along at some initial velocity of like 1 meter per second in the plus direction, and then collides, and then the other one bounces away. So it didn't quite work there, but usually what happens is the first one kind of stops, and then all that velocity goes to the second one. So that's experiment 1. So you've got some initial momentum from this cart, and this one stopped. Then they collide, this one stops, and all the momentum kind of gets transferred to the second cart. Observational experiment 2 says let's add a bunch of mass to cart A, and then sort of see what happens there. That sort of doubles it. I think I've got a bunch of these 250 gram masses. Now let's see what happens. If I do the same thing, this one comes along. Yeah. So what happens there is that this one doesn't stop and this one flies away. So before there is some velocity here, but then it keeps more of its velocity. So mass is somehow involved in whatever kind of conservation law there is here. And then the other experiment, I'm going to use carts that now, instead of repelling each other, they actually want to stick together with some Velcro. And what I'm going to do is kind of have one of them, so cart B is going to have a negative velocity, and cart A is going to have a positive velocity, and they're going to come towards each other. I'm going to try to get out of the way. Well, they kind of stop. If they go at about the same speed, I think my right hand's stronger than my left hand. There we go. So when you have two thank you. When you have two carts going in the opposite directions, then somehow those, I guess, two different velocities, two opposite sign velocities cancel out, and you get 0. So we can do an analysis of that, a mathematical analysis, if I can get back to that laptop on the left. I sure am glad you're here, because I would never be able to do this. Okay. No, the other one. Beautiful. Okay.
Push that when you want to switch.
Push it when I want to switch.
Push
Will
it
do.
when you want to switch.
Okay, awesome. Thank you.
You're welcome.
Okay. I'm having a heck of a technology day today. Does that ever happen to you? This idea of lowercase p is called momentum. That's really what chapter 6 is about. And it is this idea that when something's moving, you could take its velocity in meters per second and the direction included there and multiply it times its mass, and this gives you a new quantity, which would be, I guess, in kilograms times meters per second. And it turns out that if you do that, then this seems to get conserved. So like initial, before these two things collided, you could work it out. So this would like be just before the collision. If you work this out, P initial in the x direction is the mass of A times the initial velocity of A plus the mass of B times the initial velocity of B. So this is going to be 0.2 times plus 1. This is kilograms. And this is plus 0. So you get plus 0.2 kilograms meters per second. And that's going to be the same over here. Final P sub f, x, is also 0.2 kilograms meters per second. What's happened is that the first cart has stopped, its momentum has dropped to 0, and all of that momentum is switched to the second cart. So it is noticed by the author that the momentum just before and just after this collision is the same, so maybe it's a conserved quantity. And the idea is that with experiment 2, if you put numbers on all of these, you get the same thing. You get that P initial is just going to be MA plus V1A V initial A, plus 0, because B is stopped at the beginning. And you get 0.4 times 1.0, so you get plus 0.4 kilograms meters per second. Well, if you do this experiment and you find these final velocities, you get P final in the x direction is MA V final A plus MB V final B. So it's going to be 0.4 times 0.4 plus 0.2 times, this one ends up going with an actually faster velocity than the initial A had. When you multiply these all out, you get 0.16 plus 0.24. You add those up and you get 0.4. So this is really starting to indicate to us that momentum was conserved here. And then the final experiment is just showing that momentum is a vector quantity. So P initial here in the x direction is equal to, it's going to be plus 0.2 minus 0.2 is 0. So if I started them with the same initial velocity, same initial speed with opposite directions, the total momentum is 0, so you'd expect it to be stopped here. P final clearly equals 0 at the end because they're not moving. Okay. My voice has to last another 20 minutes here. Let's see if it does. I can feel it going, but let's see how it goes. So momentum is a property of moving things. I like to think of this big ship going through the ocean. It's got not just some velocity, but it's got a lot of mass. And those two things are somehow important. Inertia in motion. More specifically, it's the mass times the velocity. There's its equation. Oops. There's a guy running away from a big rock. A moving boulder has more momentum than a stone that's rolling at the same speed. But a fast boulder has more momentum than a slow boulder. And something that's at rest has 0 momentum. So like a 1,000-kilogram car, 25 meters per second, you just would say P is equal to, I guess it would be 1,000 kilograms, that's a 1, multiplied times 25 meters per second, comma, west, because mass is a scalar, velocity is a vector, so you just get it's equal to 25,000 kilograms meters per second, comma, west. There's a bullet traveling straight upwards. It has a mass of 0.1 kilograms, so P is equal to 0.01 kilograms multiplied times 1,000 meters per second, comma, up. That's 10 kilograms meters per second, comma, up. Small mass, but it's moving high velocity, so you get a decent-sized momentum. Let me go over, remember the pre-class quiz this morning that you did? A tiger's running in a straight line. If you were to double the mass and double the speed, that would increase the momentum by a factor of 4. Okay. Most people got that one. Which of the following quantities are units of momentum? So what's interesting is that, so clearly kilograms meters per second is a unit of momentum, but it turns out, remember from F equals ma, that a Newton is equal to a kilogram times a meters per second squared. That's how I kind of remember what the base units of newtons are. So if you multiply both sides times seconds, then a newton times a second is going to be equal to a kilogram times a meter per second squared times seconds. This second cancels the second squared. You end up with kilograms meters per second. So a newton times second is actually the same as a kilogram meters per second. Yes, question? I can see a hand up. No, I guess not. You're talking about like written questions and stuff like that. As long as your units are correct. But both of these are correct, right? Normally with assessments, if I'm marking a question, if you're correct, then you get 100%, right? So that's the way it kind of goes in physics. It's when you make mistakes that you lose points, which is also normal in physics. You make mistakes. But neither of these is a mistake. Both of these units they're just two different ways of writing the same thing. And then I think what I did with this baseball and the soccer ball, they ended up being about the same. I think what it was for the baseball, it was 0.150 kilograms times 40. And then this one was, the soccer ball was 0.5 kilograms times 12. They turned out to be around the same. On the survey, somebody asked me, is conservation of linear momentum a direct outcome of conservation of mass? I would say definitely that's not what the book is trying to imply. I think it was just supposed to be an analogy. They're very different concepts. So really, conservation of momentum comes from Newton's first law, which is that if there's no external forces on an object, it continues in a constant velocity in a straight line. So basically, it means it has constant momentum. So if there's zero external forces on a system, the system's momentum is constant. That's what the whole chapter 6 is basically trying to say. That's the big idea. And I'm going to ask you some top hat questions about this and rest my voice in a minute. But when multiple objects, this same student actually asked the second question, when multiple objects are moving in different directions, can we calculate the sum of their momenta by summing up their masses and their velocities? That's close, but what you want to do is first multiply mass times velocity. Every individual object has a momentum, so just add. So first multiply, then add. Bed mass or something. Okay. We can wait a little bit. Let me start it. Top hat question for you. A 10 kilogram cart is moving to the left at 2 meters per second. We're going to define positive towards the right. So this means that its initial velocity is negative 2 meters per second, and like v sub x, the x component. Make sense? Then the cart suddenly stops. So what's delta p, the change in momentum of the cart? And I can write down an equation, I guess. Delta p sub x is going to be, what's delta p final minus p initial, right? One thing I'm going to ask you in a minute, right now we're having more podium problems, but if I throw this tape up, is its momentum constant? Like, is the momentum as it, let's say, just after I throw it compared to just after I catch it, has that changed or is that the same? That's going to be your next top hat question. Let's look at this one. This is perfect. Thank you. Is it test? Good.
It's working.
Awesome.
So yeah,
You got it. So that was it. Nice. Thank you. Okay. So what this one was P final is 0 minus P initial, which is going to be the 10 kilograms times the negative 2. So it's actually negative 20. So it's positive 20 kilograms meters per second. So hopefully you guys figured that out, negative of a negative. This constancy of momentum looks like this. Again, initial equals final. So in your textbook, they tend to put the initial on the left-hand side, and then they sometimes put a little plus a delta equals the final. But this is a vector equation, and so you always split this up into two actual equations to really work this through. So it's kind of like Newton's second law. It says F net equals m times a, and they have vectors on the F and the a. In practice, what you do is you say that there's two Newton's second laws, which is that Fx equals max and y equals m times ay. And it's the same with momentum. It's true that the x component of the momentum is conserved and the y component of the momentum is conserved. And there's an animated GIF of a sort of recoil, I guess. So if there's a cannon and a cannonball inside there, and the cannonball suddenly goes out of the cannon, there's going to be some recoil. And that's due to conservation of momentum. The initial system had no momentum. There was some internal force, of gunpowder or something, which fired the ball out of the cannon. But then the cannon itself, which is much more massive than the cannonball, recoils backwards a little bit. Okay, so let me give you the second top hat question. Third one. This is like just true or false kind of thing. So I throw the tape upwards. Time t, it passes some height, like right after it leaves my hand, I guess. Time t2, it's coming back down again, passes that same height on the way downward. And you can neglect air resistance. How does the momentum compare t1 to t2? Same or is it different? So make sure you're voting the same way as your friend. So front row is a little split on this, but basically that's what I think is that momentum is only conserved if there's no forces on an object. So are there any forces acting on this object? It's gravity, right? And so for a projectile, momentum is always changing. And it is true, I think, that someone mentioned over here, the magnitude of the momentum is the same on the way down as it was just on the way up. But momentum is a vector quantity. And so in fact, the delta P is like 2 times V initial, P initial. It's really important to get this one. Where do I have it? Yeah, sorry, it's here. Is momentum conserved for a projectile? Definitely not. Whenever there's a net force on an object, that was not technology's fault, that was my fault. There we go. It's a combo of bad podium and flaky professor. So, okay. Whenever there's a net force on an object, its momentum is constantly changing. It's a vector quantity and the direction matters. So, don't use conservation of momentum in projectile motion problems. It's in fact, if you do the y component of the momentum there, it's positive at the beginning, it's negative at the end. So if you subtract them, you get 2 times the initial momentum. It's the delta P, the huge delta P. Okay. I've got a couple more questions for you guys. Two more questions. So, first one. 2 ice skaters, Paula and Ricardo, push off from each other. They were both initially at rest. Ricardo has a greater mass than Paula. And the idea here is that since they're on skates, let's treat the floor as being frictionless. So there's a normal force, but there's no friction force on either skater. So the only horizontal forces on either skater are the pushing forces that they exert on each other. So this is a problem. The horizontal momentum is something that you can consider to be conserved now. Okay, everybody. The one I liked was neither. Basic idea, they were initially at rest, so the momentum of the system is 0. And the momentum of the system must be 0 afterwards as well. So whatever negative momentum, the final momentum of Ricardo is, has to be balanced by a positive, equal and opposite momentum of Paula. So they're the same. So next question looks kind of similar. Looking to try clicking into this one. Same thing. Ricardo has greater mass than Paula. Which skater has the greater magnitude of velocity, so greater speed, after the push-off? Okay, before you go, let's talk about this for a second. The basic idea here is P equals M times V can be rearranged to be V equals P divided by M. So if you've given the same momenta of two objects, they both have the same magnitude of momentum, then the speed will be inversely proportional to their mass. Does that make sense? So since the mass of Ricardo is greater than the mass of Paula, he's going slower for the same magnitude of momentum. I'll post this up. Let's keep going with chapter 6. I'll see you Wednesday.